Okay, welcome back. Hopefully, again, that was an easy one for you. Solid, liquid, and gas, of course, are the three phases of matter. What's important for us to realize in this class is that the phase of a substance can be determined or identified uniquely by the state. So if I give you the state conditions, you would be able to go, hey, that's a liquid or a gas. Now, you might think, well, that's kind of intuitive. It's air. When is air not a gas, for example? But it can get trickier, particularly when we start looking at power systems. And what's important is phase change between liquids and gases, mostly between liquids and gases, not so much between solid and liquids. But that phase change is incredibly important in terms of power generation and in terms of heat transfer. And we'll see that explicitly as we start considering those large power generating systems. So now we're going to have to go through a lot of definitions. And a lot of these I'm sure you're familiar with. Here are a couple that you may not recall or you may not have been introduced to yet. The saturation state is a state which begins or ends a phase change. So if I told you you had saturated water, you would know very explicitly, quantitatively, where you were in terms of the state of the water. And again, we'll go through that in the next couple of segments. The critical point is defined as the critical temperature, is defined by the critical temperature, and it is the maximum temperature where a liquid and vapor can coexist at equilibrium. So again, these are some concepts that may be new to you. But when a system undergoes phase change, you will have both states present, a liquid and a vapor in the case of evaporation or condensation. Sublimation, you'll have a solid and a gas phase simultaneously present, etc. So those are some of the other definitions that I'm sure you're familiar with. But evaporation, condensation, sublimation, we need to remember that those have very specific meaning in terms of the phases at the initial and final state of the phase change. And in this class, that's going to point us very specifically in terms of the thermodynamic state of the system. Okay, having said that, we now want to move on to a discussion of phase diagrams. Okay, we talked about last time that we're only going to consider simple compressible substances. So again, those are substances that can only undergo expansion and compression types of work. Okay, in reality, what that really means is we're talking about simple substances, meaning not mixtures, and systems that are considered pure. So there's one species present. So that'd be like only water. And air, although you're probably thinking, hey, air actually consists of a lot of different things simultaneously. Nitrogen, oxygen, carbon dioxide, all sorts of stuff is present in air. It's the one exception that we have actually a mixture, but we treat it like it's one substance, a simple substance. And we'll see when we start looking at air properties that we actually have properties that are defined for treat air as a simple, pure substance. Okay, so let's talk about phase diagrams here. And I'm going to try and do a rendition for you, an artistic rendition here for you of a three-dimensional phase diagram using the two parameters that we were already introduced to. That's the pressure and the volume. So we'll take that a little bit into the page here. And the other axis we're going to introduce now is temperature. So here's temperature, specific volume, and pressure. And we're going to show you what the relationship is between the pressure, the volume, and the temperature for all three phases of our substance here. And I'm not going to identify the substance just yet. I'll get back to you on that. I'm going to tell you that it's fairly generic. Okay, so as we get this sketch all drawn out for you here. Okay, so now we have something to work with. This region, where we have very low specific volumes, or if you prefer, very high densities and very low temperatures and nominally high pressures, is the region of solid phase for our substance. If we increase the temperature, so let's walk along this axis here, we see that we know that we'll transition from a solid to a liquid. So this is the region of liquid phase, and then as we keep moving in even higher temperatures, we should transition to the gas phase region. This region here on the PV diagram is the solid vapor region. And in this region, both solid and vapor phase, because remember this is the gas phase here and this is the gas phase here. So I'm sorry, I'm using gas phase and vapor interchangeably. The gas phase or solid, we know we have to transition from the solid to the gas phase, and in this region we have both solid and vapor phases present simultaneously. So here, where we're bridging between the liquid and the gas phases, we know that we have liquid and gases present. So liquid and vapor region, if you prefer. Okay. These lines are very important and very specific. These are the lines that I just referred to before, which define the saturation point. So this line is the line of saturated liquids. Okay? And on this side, we have the line of saturated vapor. Okay? And they meet here at the apex of this curve is the critical point. Okay, remember we define the critical point as a point above which we no longer have a distinct transition between the gas phase and the vapor phase of the mixture. The critical point is uniquely defined for each substance. So, critical point. Once you know the critical point, in terms of the temperature, it uniquely defines everything else, all the pressure, the specific volume, all the other properties associated with the system. This region here, this liquid-gas region, is often referred to as the vapor dome or the saturation region. So this is the vapor dome. And you can see how it gets that name because it's got a dome-like shape to it here, or if you prefer, the saturation region. This figure that I've shown you here is a generic figure that could be used to describe any substance as long as it is a substance that expands upon freezing. And you can tell that because of that little knee in the solid-liquid interface. So if we had instead of having the curve or the state diagram move to the left here, if it instead moved to the right, you would have a substance that actually contracts upon freezing. Okay, so that's how you can tell. Getting a little bit into the detail there. These regions are regions that we have single phases. So these are single phase regions. And again, to clarify here, the gas and vapor are both, that's gas, just two different ways of saying the same thing. This isn't a mixture of anything. This is just saying, hey, when you have a gas, we'll also call it a vapor. I'll, again, use the words interchangeably. Now, one little phrase that we use often in thermodynamics is fluid. We talk about the fluid being here or the fluid being there, or we move the fluid up and down or compress it. And fluid is pretty generic to not just include liquids. It also includes gases. So don't assume that if you're told the fluid moves in this direction that you have a liquid. Okay? We know that actually, or in this class, that includes the vapor phase as well. Okay, so if these are single phase regions, These regions where you have mixtures of liquid and gas, solid and vapor, these are two-phase regions. Okay. And what's really important for us to understand is, remember we had our rule for how you define a state uniquely. We said you need two independent, intensive thermodynamic properties to fully define a state. The key here is the independent, the word independent. In the two-phase regions, pressure and temperature are not independent. Okay. That's really, really important. Within the two-phase regions, we cannot use pressure and temperature to uniquely define the state conditions. And pressure and temperature are the variables we most like to use because, well, you should ask yourself, why do we most like to use pressure and temperature to define a system? I'll tell you. It's because they're the easiest to measure, and they're very tactile. We understand high temperatures and low temperatures. That has a very, we get a very visceral response to that. We understand if we have a high temperature system, we know temperatures very well quantitatively. Is a 100-degree fluid, 100 degrees Celsius fluid a high temperature? Is that something that's going to burn? Is it safe? Does it have a lot of energy? We have a good understanding of that. Same with pressure. We understand a lot. We can measure it very well and very accurately. Okay, so pressure and temperature are go-to variables for defining a state. Unfortunately, they are not independent once we go into the saturation region, into the vapor dome. And under those conditions, we're going to have to invoke other thermodynamic properties in order to uniquely define the system. Okay, so this is my clever 3D rendering of a phase diagram. In reality, they're kind of hard to work with. So what we've been looking at is a projection, or a cut, if you will, of the PV diagram. That's what we've been using for our past couple of examples. So imagine if you took a slice through this on the PV axis, and you would say, I understand. For a particular temperature, I can define a PV diagram. Or, if you prefer, I can look at a projection, a projected two-dimensional rendering of the 3D phase diagram. Okay, but the 2D renderings are a lot easier for us to understand, and that's what we typically use. So, but we do need to understand that all of the properties are interrelated, and we want to characterize systems so that we have a lot of information about the state. So no matter where we are, pressure, temperature, density, we know how to quantify the state of the system. Okay, so let's talk about 2D phase diagrams, because again, that's what we're mostly going to use. And we'll just take a couple of examples here. We don't want to get too tied up in this, because what we'll do is we'll keep introducing phase diagrams as we do our examples. So we'll again, every moment is a teaching moment. So we'll get plenty of opportunity to practice our phase diagram skills. So let's take a look at the one that we've been using most. Let's take a look at the PV diagram. Okay, so if we took that previous three-dimensional image, and again, we take a slice of it or a 2D projection of it, what we would see is something that looks like this. Okay, so here to orient you, here's my critical point again. So here's my critical point. Okay. And this line defines the boundaries of the different phases. So, oops, sorry, that's a straight line. In this region, again, where we have the highest densities and nominally high pressures, we have the solid phase region. Okay, we know as we move. Well, I don't have temperature on here yet, so that's a little trickier for us to just look at and intuit. But in this region, we have the vapor phase. In this region, we have solid plus liquid. Okay. And then here's my liquid. And remember, above the critical point, this is important, above the critical point, we essentially have no transition between liquid and vapor. Those are called supercritical fluids. So above that critical point, we have the supercriticals. And they're neat because they act neither like a gas nor like a liquid entirely. So they are other. And they have some really neat properties, and there's been a lot of work in all sorts of different systems to use those properties of supercritical fluids to enhance the performance of different technologies. So they're a neat and very topical area. So what I want to show you is what isotherms look like. So isotherms are lines of constant temperature, as that might imply. So let's see if I can get it to stay with me. There we go. Okay, so an isotherm on these diagrams are going to look like this. Okay, so these are isotherms. Again, lots of definitions. So an isotherm is a line of constant temperature. Okay. Isobars are lines of constant pressure. And isometrics or isomers are usually lines of constant density or constant internal energy. But the isotherms are the ones we really care about most. So we're looking at this diagram, and what I want to do is kind of this thought exercise of let's slide down along one of these isotherms and see what that means. So, or it might be a little bit more intuitively, make more sense if we do this. Let's go increasing pressure. So we'll start in the vapor phase here, and we're at some, low-ish pressure at some known density. And as we increase the pressure, we can see that the density of the fluid increases, or if you prefer, the specific volume decreases, and we slide along this line. I'm going to increase the pressure at a constant temperature. So we're going to slide along this isotherm, and we're going to reach the saturation point for the vapor. So again, this is the saturation point. And what we have is a saturated vapor. Okay. Notice that once I define the temperature, there's one saturated vapor point. So if I tell you you have a saturated vapor at this temperature, you have uniquely defined this point. So we have our two independent intensive variables, the temperature, and I've told you it's a saturated vapor, which is, we're going to define that in terms of very special variable coming up, but I'll give you a little bit of a hint. It's going to be the quality of the mixture. And the quality of the mixture, if for a saturated vapor, is 1. Okay? So that uniquely defines this point. Then as we further increase the pressure, what's important for you to see is that while we slide along this isotherm, we pass through this region where after we increase, once we fully condense the vapor into a liquid, we then increase the pressure. Okay, the pressure increases in the system. But during that process, where the vapor is condensing, the pressure and the temperature are not independent. They are dependent variables. So that's just like I said before, in the vapor dome, okay, pressure and temperature are dependent. Okay? So again, and then as we increase the pressure, we do see the system fully condenses, and then we should pass through the solid and liquid region, again, through a phase change, and then into the solid region. Okay, so this is what happens as we slide along that isotherm. Okay, you can do the same thought process of, let's say, moving in density space for a constant pressure. You can do the same thought process for a constant volume. Those are all good things for you to kind of think through what would happen as, for example, if I said I have a constant density, and as I increase the pressure, what would I see? What would happen to my mixture? Okay. The only other thing that I want to cover on this particular PV diagram is we know that these are lines of isotherms, constant temperature. So I'm going to call this one, I'm going to just label it T for right now. And I'm going to call this one T2. And we know they're two different temperatures. What I want you to think about, and maybe we can come back for this for next time, this will be our closing question for you, is which temperature, I'll call this temperature A, and this is temperature B. Which one of those is higher? So it's not only important for us to understand what lines of constant temperature look like, but also what direction are they moving in terms of the magnitude? So is TA greater than TB, or is TA less than TB? And then next time what we'll do is we'll answer that question and we'll consider yet another state diagram. Thanks.